All right, welcome back. This last video from section 5.1 is going to take a look at some specific behaviors and terminology related to sequences. So the first thing is let's take a look at these definitions here in the next box. It talks about definition of what it means for a sequence to be increasing or decreasing. I think that's pretty straightforward. As far as what you know from calculus, when the terms rise in value, they are increasing. When they decrease in value, they are decreasing. The easiest way to do that, to show that a function is increasing, or not a function, but to show that a sequence is increasing or decreasing is actually with the derivative, right? Because if the derivative is positive, a function is increasing. If it's negative, it's decreasing. All right, so any function that is increasing or decreasing we call monotonic. And then the other thing we want to talk about is a bounded sequence. So bounded, we can talk about being bounded above or bounded below. It's bounded above if all the values in the sequence are less than some specific value m, and it's bounded below if all the values in the sequence are greater than some value. And if it's bounded above and below, if the sequence has a bound, some high value and low value both, then we call it a bounded sequence. All the terms are within some upper and lower bounds. And then there's one theorem here. It says that if a sequence is a bounded sequence, and there exists a positive integer in O such that a sub n is monotone, so meaning it's increasing or decreasing for all n greater than n0, then we say that it converges. Okay? So if we have a bounded sequence, remember, bounded means that it's bounded above and below, right? A bounded sequence is one that's bounded above and below. So if it's bounded, if it has a cap on the top and a cap on the bottom, and it's monotone, which means it's increasing or decreasing, then it must converge. It must approach some value. So let's take a look at a few examples here. Example 5 says, determine whether the sequence is increasing, decreasing, or not monotonic. And then it says, is the sequence bounded? So let's just write out a few terms here for this first sequence. Notice that they're all negative. First term is going to be -1. We have -4. -9, -16, -25, and so on. Notice that the terms are getting smaller and smaller and smaller, which is going to make us think that the sequence is what? Increasing or decreasing? And hopefully you said decreasing. Yeah, terms are definitely getting smaller. And if it's decreasing, that means that it is also what? From the definitions above, it means it's monotonic. Okay. And we could also show this with the derivative. So we could say if f of n is equal to -n squared, then f prime of n is -2n, which is always going to be less than 0. Right? At least when n is positive integers like we have with a sequence. So we could say it's always going to be less than 0 for all positive integers n. So the sequence is decreasing. We could also say a sub n is bounded above, and we can say that because all the terms, right, aren't all the terms less than or equal to -1 for all n greater than or equal to 0? Or actually, I guess we should say 1. The first term is 1. For all n greater than or equal to 1. In other words, -1 is that upper bound. That first value is the largest value in that sequence, so it's bounded above. Now, it's not bounded below because the terms keep getting smaller and smaller and smaller. Okay, let's look at another one. A sub n equals -1 to the n plus 1. This is one of those sequences that is bouncing back and forth, right? So the first term when n equals 1 is +1, and then -1, and +1, and -1, and so on. Is that sequence increasing or decreasing? Well, we can't say that because it's not, each term is not successively getting bigger or smaller. So in this case, we would say it's not increasing or decreasing, which means it's not monotonic, right? Now, is it bounded? Well, yeah, because the biggest value is +1 and the smallest value is -1, so it's bounded above and it's bounded below. Now, remember, that was one of the definitions. If it's bounded above and below, we say it's a bounded sequence. So we could say A sub n is bounded above by 1 and below by -1, so A sub n is a bounded sequence. Okay, so that's a bounded sequence. We got one more here. A sub n equals 2 over n squared. Again, let's write out a few terms so we can see what's going on here. First term would be 2. The next one's going to be 1/2. We have 2 over 3 squared, which is 2/9. We have 2 over 4 squared, which is 2/16 or 1/8. And so on. And does it appear that this sequence is increasing or decreasing? Well, it sure looks like it's decreasing, right? It doesn't look like those terms are getting smaller. But again, we could also verify that. If we let some function represent 2 over n squared, which remember is going to be 2n to the -2, then what's the derivative? F prime of n equals -4n to the -3, which is -4 over n cubed. And so notice that this is always going to, again, be less than 0. The derivative is always negative, which means it's always decreasing. So it's decreasing for all n greater than or equal to 1. Another thing we can take a look at is, so we can see, it looks like these terms are approaching as n approaches infinity. Well, what's the limit as n approaches infinity of 2 over n squared? Well, that's 2 over infinity, that's 0. So it looks like all the terms are going to be approaching 0, which means it's bounded below by 0, and then of course it's bounded above by 2. So the sequence is bounded above by 2 and below by 0. So A sub n is a bounded sequence. You can say that because it's bounded above and below. All right, and so that's going to do it for example 5. We have one more example here. This should actually be example 6, right? It's a little typo. What are some recursive sequences? Well, recursive sequence is when each term in the sequence is related or built on previous terms. So it says find the first 10 terms of the Fibonacci sequence. It says the first term is 1, the second term is 1, and then each term after that is going to be related to the previous term. So we could say that a sub 2 is equal to the sum of the two terms before it. So well, actually I guess I would call that A3. It's my fault. So I should say A3 is the sum of A1 plus A2, which in this case is 1 plus 1, which is 2. So that means A4 is going to be the sum of the two terms before that, which would be 1 plus 2, which is 3, and so on. A5 is going to be the sum of 2 and 3, which is 5. And this is actually easier to see if we just start writing out this sequence. So the Fibonacci sequence starts with 1, 1. You add those two terms, you get 2. You add 1 and 2, you get 3. You add 2 and 3, you get 5. 3 plus 5 is 8. 5 plus 8 is 13. 8 plus 13 is 21. 13 plus 21 is 34. And so on. Am I up to 10 yet? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. And it keeps going. It's also an infinite sequence. So that is an example of an infinite recursive sequence. And that's going to do it for section 5.1. And I'll see you in the next video. Thank you.